So we have been studying the sphere always since class 8th and class 9th. The surface area of a sphere is 4 pi r square and the volume is 4 by 3 pi r cube. And today we are going to derive this formula and we will be making use of the integral calculus. And more important than deriving this formula, I wanted to show you how we tackle any problem using integral calculus, which has a lot of use in engineering, in physics, in many other places. So let's draw a sphere. It looks like this, and that its radius is capital R, and we cut the sphere right at its center. If we imagine there is a circular strip, if we are cutting it right at its center, into making it into two halves, and then on the top half we take a small strip. That is how we do all of this integral calculus related problem. Whenever we need to find the, let's say, surface area, we don't know the whole surface area. There is no fixed formula because things are varying in a very gradual fashion. And when there is a very gradual fashion, there is no fixed formula. We need to take one thing at a time, one small piece at a time. And what we have taken here is this small piece, and we will find the surface area of this small piece, outer surface area. And then we need to add these small pieces, the surface area of these small pieces, all the way from the bottom, and add those small pieces area all the way to the top, which is exactly what is integration about. So let us say this radius is capital R, and to find the surface area of this small piece, we need the length of this circumference, and then we multiply it by the width of this thing, this strip. The width is this portion of this arc here. Sometimes you may think that if we, for example, could put a line here and call it H, that could be the strip, which would be false. Because if you take this height along the height, this small strip, that is going to be less than the surface. The surface is a little curved, a little bulgier than this height. Height is smaller, curve is bigger. You need to take this length of this curve and multiply it by this circumference 2 pi r. So let this radius is small r, and if we call this small area dA, then dA will be given by this circumference 2 pi into 2 pi r multiplied by this small length, let's call it ds. Essentially, we are measuring this length all the way from here to here. Let's call this length S for our understanding. S is nothing, a differential S, a small part of this arc S. To solve this problem, what we need to do is here now. We need to integrate this area from here to here, and it will be better probably. Now R is varying with as we move from this here to here. As this small ds is also varying from here to here. So we need to express these things R and S in one single variable. We cannot have two variables. The constants are fine. It will be better if we join this line and introduce a new variable theta. How do we define theta? Theta is nothing but this arc divided by this radius, or S divided by R. We can write R theta is equal to S. And if we differentiate this thing, we get R d theta is equal to ds. We can also visualize it like this. Let us along the angle make another line, radial line like this, and call this angle d theta. What is the definition of this angle? Definition of this angle is this arc divided by this radius, ds divided by r. So whether you look at like this or you look at like this is pretty much the same thing. And the intention of introducing this is to replace this variable ds, which we cannot measure, which we don't know how it's varying, with a more known variable theta, which varies from 0 to pi by 2 as we sweep this angle. So this becomes 2 pi r into capital R d theta. The next thing we need to do is express this r in terms of theta, because we need to have only one variable and only then we will be able to integrate it. To do that, this angle is theta, this angle is also theta. And let's now express r in terms of theta, and for this we have this triangle in which we can write cos theta is equal to base small r divided by capital R. So we have cos theta is equal to small r divided by capital R. We can send r to the left hand side, becomes small r is equal to capital R cos theta. And let's differentiate this whole. No, we don't need to differentiate this one. We just substitute for r, we substitute r cos theta. This becomes 2 pi into capital R cos theta into r d theta. So this becomes 2 pi r square cos theta d theta. This is our dA. The dA is this small area. The next thing we are going to say is that the total area S will be equal to 2 times the integral of dA, as theta varies from 0 to pi by 2. This dA is this small area. If we add up all these areas from here to here, it becomes this total hemisphere here. From theta varies from 0 to pi by 2. And we can do twice of this area, it will give the whole hemisphere area. Another way to do was to vary this theta from minus pi by 2 to plus pi by 2 and not do this 2 multiplication sign. Both of them are the same thing. This becomes equal to 2 times integral of 2 pi r square cos theta d theta. 2 and pi and r, they don't vary as theta varies from 0 here to here. R stays constant, pi stays constant. And this is, therefore we can do these things, these three things I become 4 pi r square integral of cos theta d theta, as theta varies from 0 to pi by 2. So the cos theta integral is sine theta, and here theta varies from 0 to pi by 2. Then theta is equal to pi by 2, sine pi by 2 is 1, and theta is equal to 0, sine 0 is 0. So this becomes 1 minus 0. This 4 pi r square 1 minus 0. And this becomes equal to 4 pi r square. And we have proven that the surface area of a sphere is 4 pi into capital R square. If you want, you can take a break and try to solve it on your own. And if you make a mistake, you can come back and check it again. So the next part of this lecture will be the volume of the sphere. We can similarly try to derive the volume of this sphere. We'll get rid of dA. We don't want to find this area, but other than that the picture will be same. Once again we will consider the same strip, this, but instead the outer surface area, we are trying to find the volume of this thin a cylinder. It looks like a cylinder, and in that cylinder, the height of that cylinder, let us say this height is h. Then the height of this cylinder, we will call it dh. So if let us introduce another temporary variable dt, which is the volume of this cylinder. Let's call it dv. Doesn't matter. dv is the volume of this cylinder. That will be equal to the area of that base, area of the base, which is going to be pi r square, multiplied by the height of the cylinder, which is dh. This is that one small strip. Right, this is how we do all the integral calculus problem. We find this value of the thing that we need to find for a very small part, express this in terms of those variables, and then we integrate the whole thing. The key thing is how to express those variables in terms of one single variable that we can integrate. And here we are again, our final one variable will be theta, and theta will vary either from minus pi by 2 to plus pi by 2, or from 0 to pi by 2, and then we take twice of that. Again, how do we express r in terms of capital R and theta? We have the same formula. Cos theta, we had done it earlier. Cos theta is equal to small r divided by capital R. So small r is equal to capital R into cos theta. This is equal to pi r square cos square theta into ds. We are doing one thing at a time. Equal to pi r square cos square theta. How about dh? How do we find dh? For that we have this equation sin theta is equal to h upon r, this capital R radius of this here. Sin theta is equal to h upon capital R. We can take r on this side, we get r sin theta is equal to h. Now we can differentiate this and we get r cos theta d theta is equal to dh. And from here we take the value of dh and substitute it here. R cos theta d theta. The next, this is our dv. So we are able to express dv in terms of only one variable, the theta, that we can integrate. Equal to pi r square into r is r cube, and this is cos cube theta d theta. This is dv. Now if I integrate, I can write the volume of cylinder, volume of sphere, will be equal to integral of 2 times of dv, as theta varies from 0 to pi by 2. We take this small volume, add up all these small volume from here to here, and then multiply them by 2. And this integration is nothing but the addition of these small pieces. This is equal to 2 times integral of pi r cube cos cube theta d theta. Pi and r cube stay constant, so we can take them out. This is 2 pi r cube integral of cos theta cube theta d theta, as theta is from 0 to pi. To integrate cos cube theta, we use the trigonometrical identity of cos 3 theta is equal to 4 cos cube theta minus 3 cos theta. And if you have forgotten it, you can derive this quickly using the formula cos A plus B is equal to cos A into cos B minus sin A into sin B. Instead of A, write 2 theta. Instead of B, write theta. You get cos 2 theta into cos theta minus sin 2 theta into sin theta. Then express cos 2 theta in terms of cos theta. Express sin theta as 2 sin theta into cos theta. And if you do a couple of more things, you should be able to get this result. From here, we get cos cube theta is equal to 1/4 of cos 3 theta plus 3 cos theta. And then we can substitute this whole thing over here. So from here, we come back here, we have the volume equal to in 2 pi r cube integral of cos 3, we put 4 here, right here, cos 3 theta plus 3 cos theta. D theta, as theta varies from 0 to pi by 2. This is pi r cube divided by 2. And now we are trying to integrate this. Cos 3 theta is sin 3 theta and then divided by this 3. Sin 3 theta divided by 3. And cos 3 cos theta is 3 sin theta. Theta varies from 0 to pi by 2. Oh. Duster. We need to make some more space here, but I think we are very close. So this is pi r cube divided by 2. Sin 3 pi by 2 is sin pi plus sin pi by 2. And sin pi plus theta is minus sin theta. We can write it as, and sin pi by 2 is 1. So this is minus 1 upon 3 and then plus 3. Sin pi by 2 is 1. So plus 3 and then minus this 0 and then minus 0. So this becomes equal to pi r cube divided by 2. 3 into 3 is 9 minus 1 is 8 by 3. And this becomes 4. 2 into 4 is 8. Is 4 by 3 pi r cube. So we derived the formula for the volume of a sphere. We derived the formula for the surface area of a sphere. But more importantly, we knew tricks to how to solve any problem using integral calculus. You'll have to use these things in your engineering problems and physics problems and everywhere to derive more complicated things and formula in this sphere. Thanks for taking a look. And if you have any comment, anything about it, if there is any mistake you think fail or you need any more explanation, write in the comment section. Thank you.